few questions. I think we completed the application part of electrochemical series, right? So
Yes,
there
sir.
is this point why we cannot put the metal solution in a metal container whose SRP is low. Why we cannot do that?
Sir, it is because, like for example, copper and silver.
Mm-hmm.
So then it gets corroded. So that's why we can't put it.
You are right. Okay. So today what we are going to do is we are going to start a very important topic, which is Nernst equation, and you are going to get a question from this topic, and the chances are like 90%. So you have to focus on this one. So before we start, I would request you to please turn on your webcam. So you can start. Today's topic is going to be the Nernst equation, and it is very important. We are going to do some questions as well. Please turn on your webcam. Okay. Mhm. So Nernst equation. Basically, we have studied about two things so far. The first one is we studied about free energy, Gibbs free energy, right? That the drop in Gibbs free energy is the thing which is basically converted into the electricity while we connect the two, like basically make a cell or circuit. And then on the later part, we studied EMF, electromotive force, right? So what Nernst equation do? Nernst equation helps us to basically create a relationship between EMF and your free energy, Gibbs free energy. So what it is, let us talk about it. Basically, we know what is work. Work is charge into potential. You might have heard it in your physics class, right? So what is work? Charge
Yes, sir.
into potential. Hmm. So basically, work done can be related with any sort of energy, right? Work done can be related with any sort of energy. So if we are talking about Gibbs free energy, then we can relate it with in terms of work done as well. So I can replace my work as delta G, which is change in Gibbs free energy. And this negative sign is denoting that the work done, that the process that we are performing is a spontaneous process, right? So basically what is charge? Charge is measured in Faraday, and this N is signifying the number of charges, right? NF, and the potential, it is represented by E. So we can convert our work done formula into something which is relating our Gibbs free energy as well as our EMF. So let us see. We can say delta G is equal to minus NFE, right? This is a very important formula that we are going to use while we'll be driving the Nernst equation. Okay. What else?
Yes,
If
sir.
what is the significance of this not or dot? If I am putting this sign over any formula, what does it signify? We have done these type of like formulas before, and like in the last lecture I
Uh,
told you about.
like standard, like at
Very
STP.
good, very good, very good, very good. Standard temperature and pressure, right? Standard conditions. If you are using that not sign, it is basically signifying that the condition are standard. What do you mean by this? That the pressure and temperature and your concentration are going to be standard, right? So let us drive our Nernst equation. Nernst equation basically do what? Nernst equation gives us the relationship between our EMF, temperature, and the concentration of the ions that are present in our solution or our basically system. So from thermodynamics, in your class 11 thermodynamics, you must have seen this formula, right? So basically we have to start with this formula. What is it? What it is? Delta G is equal to delta G naught plus RT natural log theta. Okay. So if you have to replace natural log into log, what you multiply it by? 2.303, right? Ln is nothing but 2.303 log. Do you know this?
Yes, sir.
Okay. What else? What else we can do? Now we just drive something that your delta G is nothing but minus NFE. So we are going to replace our delta G as minus NFE here. N minus NFP, not here because the not term we are using it. Okay. So after deriving this formula, or I would request you to see this first. From here to here, we have reached. Is there any part where you are like thinking about how this happens? Try to see it. We started with this thermodynamics formula that we know. We have studied it in our 11th class, and we just did what? We just replaced our delta G with our NFE, and we expanded our natural log into log by multiplying it by 2.303.
Yes, sir.
Now, what you are going to do is you are going to divide the whole equation by minus NF. If you are doing this, what you are getting basically? You are getting this NF term cancelled out, right? And you are getting this E. And this E is basically your EMF. So after dividing this entire thing by minus NF, you are getting this formula. Okay. And this formula is your Nernst equation formula at non-standard state. But what if you are taking standard state? Suppose in this formula, what you are saying, the temperature is given, R is given, Faraday is given, right? This formula
Yes, sir.
is valid when your conditions are not standard. Suppose they have given you a specific temperature, let it be 100 degrees Celsius. Let it be anything apart from the temperature which we consider standard, which is 298 Kelvin. Apart from this temperature, if they are giving you any question, you have to use this formula. And like the better thing, like the good thing about this is you will hardly see any question where you have to use this formula. Most of the question that you will be dealing with, you have to use this formula because the condition would be in standard state. So after deriving, you got this formula. And if you are putting the standard temperature and like your Faraday constant value, after solving this formula by basically replacing these values, you are getting this ultimate formula, which is E, which is EMF is equal to E naught, which is again EMF but at standard state, minus 0.0591 divided by N into log theta. This theta is basically your reaction quotient. Reaction quotient, what do you mean by this? In any chemical reaction, uh, when you are basically uh, taking the concentration of your product to the stoichiometry, dividing it by the reactant's concentration to the stoichiometry, this is your reaction quotient. You must have seen this in your equilibrium chapter.
Yes, sir.
Okay. So this is the final formula that you have to learn. I would suggest if like in your exam they are trying to give you a typical like tough question, they might give you some basically given temperature and other stuff. So you can also learn this formula as well. Right?
Yes, sir.
Just see this for a few minutes and then let me know if there any term or anything that you are not able to understand.
Done, sir.
Okay. So what is Faraday? What is this F? This F is basically Faraday constant. And what do we mean by Faraday constant? It means charge on 1 mole of electron. How much is 1 mole? How much is 1 mole? 1 mole is
Uh,
basically this thing, 6.022 into 10 to the power 23.
yes, sir.
And how much charge is on 1 electron? A charge on 1 electron is 1.6 into 10 to the power minus 19 coulomb. So what do we mean by Faraday? Faraday basically means the entire charge on 1 mole of electrons. So after solving this, you are going to get this formula, or sorry, value. After rounding off, you can use this. So this is basically your Faraday constant, which is a constant, which is coulomb per mole, which signifies how much charge is on 1 mole of electron, right?
Yes,
So
sir.
basically, if you put this value here, And for temperature, if you are putting 298 Kelvin, and for this real gas constant, you are taking the value, the constant value as again, then after solving this, you are going to get this thing only. Okay, the R is 8.314. N, what is N? N is the number of electron in balanced chemical equation. And the temperature, the standard temperature is 298 Kelvin. Is it making sense?
Yes, sir.
Okay. So how we are going to use our nurse equation while solving our questions which are given in the NCERT. So let us see the normal term and normal approach that we should follow. Suppose this is a normal reaction. Okay. What you are observing here, there was something, some metal in aqueous state, that is +2 oxidation state, and it is gaining some electrons, 2 electrons, and converting into a solid, right? So if you have to use Nernst equation, what is the formula? The formula is this one. Your E cell is basically nothing but E naught minus 0.0591 divided by N log reaction quotient, right? So can you tell me one thing, like in this reaction, what is happening? Is it a reduction reaction or oxidation reaction? This one. Are you observing reduction or oxidation here?
Uh, Reduction.
Good. So if you are calculating the E cell, is it going to be a reduction potential, E reduction potential, or E oxidation potential? Obviously, it is going to be E reduction potential. This E
Yes,
is
sir.
basically EMF, and this RP is signifying that we are observing a reduction. Okay. Now, how do we know that this N is 2? Because in a balanced chemical reaction, the number of electron that we are observing is 2. Is it not? And
Yes, sir.
this theta that we have used here, how we are going to basically solve it? Theta is what? Theta is your product concentration. This square bracket basically signifies that you are taking concentration, right? Divided by reactant key concentration to the power stoichiometry, whatever the stoichiometry is. Now, the important thing that you should remember, we are going to take only the concentration of aqueous entities. If we have given a solid or a liquid, then we will take the concentration as unity. So here what you are observing, this is a solid, this thing is a solid. So if you have to write the reaction quotient, then you will write it like M solid divided by like the stoichiometry is one, then we are basically putting the one over above it. Then here what we have, M 2 positive to the power 1. Now, as I told you that solid and liquid has unity concentration. Then after solving this, we will get one here and the concentration of the aqueous solution like this. So this is the way you have get the value for theta here. So what you can learn from here is only the aqueous entities you will be using the concentration, and they might give you the concentration. But for solid or liquid, you will have to use one as unity. Is it clear?
Yes, sir.
Sure.
Yes, sir.
Okay, let us take a few more examples. This is basically your hydrogen, right? Hydrogen electrode. So what is happening here? Is it a reduction or oxidation reaction?
Oxidation.
Good. Now, if it is oxidation, how you're going to represent the E cell? You can represent E cell in this manner. It is showing that you started with H2 and it is converted into H positive. That means it has lost some electron. Okay.
Yes, sir.
Now, what is E naught? We studied for standard hydrogen electrode, SHE, the E naught value is what? 0 or not? It is a reference electrode.
Yes, sir.
For SHE is a reference electrode. We use this to determine the potential of other half cells. So the potential for this one, the EMF for this one is going to be 0, right? And this 2 comes from this 2 electron. And what else do we have here? See, try to see it carefully. Here we have aqueous, right? In the product side, we have 2H positive aqueous. So for reaction quotient, what you are going to do is you are going to put the product H positive and the stoichiometry is 2 to the power 2, right? Now, on the reactant side, what do we have? Gas. Gas. For gas, I told you that the concentration of gas is measured in terms of pressure. The concentration of gas is measured in terms of pressure, right?
Hello, sir. Can you hear me?
Mm, just give me a second. Ah, now can you mm, say something again?
Uh, yes, sir.
Hmm. Okay, so what I think you might had some network issues, so let me repeat what I was saying. For I hope this formula is clear till here. How we get this? We have a simple formula, we just put the value, right? Now for the reaction quotient, I was telling that in the product side, you have H positive in aqueous state. So how you are going to use or how you are going to show the concentration of H positive, you are going to use the bracket, the square bracket. And inside this, you have H positive, which is signifying basically the concentration of H positive, right? And the stoichiometry here is 2. So you have to put the stoichiometry at the power. You have to show it as a power, right?
Yes, sir.
And, and. For your gases, in the solution chapter, I told you that the concentration of gas is measured in terms of pressure. So here, if you have something which is in gaseous state, you have to use the pressure term. You have to use pH2 like this, right? Gas may, here I have written, gas may, pressure is equal to concentration. So this is your reaction quotient formula for your gas. So this is what you are going to get after solving H positive. This is just this is like how you can say a normal approach how you're going to start solving the nurse equation questions. We have not get any answer yet. I'm just teaching you the approach. I will take some specific questions where we are going to get the answer as well. So for now, mm, try to build the approach how you're going to use nurse equation in questions, right? Now let us see
Yes,
this one. What do we have here? It is a basically redox reaction. Reduction and oxidation both are happening simultaneously, right?
yes, sir.
So this is your E cell, this is your E naught cell. How you got 2? Because the number of electrons that are exchanged here are 2. And in the product side, you have Zn2 positive aqueous. This is solid. So for solid, we don't consider. If you are even mentioning CuS, it is correct. But after solving it, you are going to get 1. So whether you show it or not, it doesn't matter. On the left hand side, you have aqueous. You showed aqueous, and this is solid. So you don't have to show it because it is going to be a unity. So this is how you are going to solve the Nernst equation for redox reaction. Right? Do I need to tell you how I know the number of electrons are 2 here? This is basically a net reaction which we get after solving the reduction half and the oxidation half. Do I need to show you how we get the N is equal to 2?
Yes, sir.
Okay. See, if you see this one, what is happening? This is going from Cu2 positive to Cu solid. So is it a
Yes, sir.
reduction or oxidation?
Oxidation.
Are you sure? It was initially in Cu2 positive. Now after reacting or
Reduction.
after
Reduction.
reduction, right? So it was like this reduction half cell, right? Reduction half cell. It was like Cu2 positive plus 2 electrons gave Cu solid. What about the oxidation after? This thing is getting oxidized.
Yes,
Zn
sir.
from solid is going into Zn 2 positive plus 2 electrons. So after reduction half cells and oxidation half cell, you are going to get a net reaction. You are basically going to subtract the number of electrons and you are going to simply write it like Zn solid plus Cu2 positive aqueous gives Cu solid plus or Zn plus 2. Right? This is how we got the n is equal to 2.
Yes, sir.
Is it making sense?
Yes, sir.
Now, let us take this last example, then I'm going to show you some questions. Right? In this reaction, what you are observing? This Mn was in +7 oxidation state. How? To calculate oxidation state, how we proceed? Let the metal that you want to find the oxidation state for, let it be X. Then for oxygen, how much basically charge one oxygen atom causes? So it is -2. How many oxygen atom do we have? 4. One is contributing -2. And the overall charge is -1. So -1 like this. X minus 8 is equal to -1, which is going to be X is equal to +7. So by this approach, you know that the manganese is having a +7 oxidation state. So what is happening? From +7 oxidation state, it is going into +2 oxidation state. So it is doing a reduction or oxidation. Is
Uh,
it? Mhm.
Reduction.
Good, reduction. But whether this reaction is this one, balanced or not, is this reaction balanced or not? And this is happening in acidic medium. You must have
No, sir.
seen, no, right? Because on the left hand side you have 4 oxygen, on the right hand side you don't have any oxygen. So these type of chemical reactions are balanced. You might have seen this in the redox chapter in your previous class, right? How you do this? You have to add H2O. Basically, the number of oxygen atom you have on the left hand side, you have to add the same number of H2O on the right hand side, right? After this, you have to balance the number of hydrogen atoms on the corresponding side as well. So first what you did? Here are 4 number of oxygen. You added 4 H2O. Now, after adding H2O, what you are getting in excess, which is H H positive basically. So here we have H2, 4 into 2, 8. So you have to add 8 H positive on the left hand side. Now this reaction is chemically balanced. And for this reaction, you are going to apply the Nernst equation. So what is important for Nernst equation? Equation balance karna is very important. Without balancing the equation, you cannot apply the formula. If you are doing that, you will get the wrong answer. Okay. So to
Yes,
this
sir.
equation, you will apply your Nernst equation. This is your product. This is your reactants. And this is how you're going to solve the question. And this is your number of electron, which is 5. Right.
Yes, sir.
So I think you are traveling right now. So you won't be able
Yes.
to open your book. So let me do one thing. Let me see, take some questions directly from the net. No, it is other. Mm. So let us take this example and let us try to solve it. So what is given here? You have to write the Nernst equation uh, and EMF of the following cell. So what you are going to do? So first of all, let us take this first example. What is happening? This is the general notation of, like, if you have a cell, you can with the help of IUPAC, you can write it like this in short way, right? So you don't have to like basically write the whole reactions. You can write it in simple way. So with this data, what you can determine, what you can get, you can see on the left hand side what we usually have anode. This is your salt bridge followed by cathode. At anode, what do you observe mostly? Like always, at anode, what is happening? Oxidation or reduction? Am I audible, Ali?
Yes, sir.
Okay, so at anode, what you always observe? Oxidation or reduction?
Reduction.
Nope, oxidation. What is happening here? This is your anode. It is converting into solid to aqueous. So it is losing electron, right?
Yes, sir.
This is your salt bridge. And on the right hand side, you have cathode where you will observe reduction. So with this simple data, you can derive your chemical reaction. And with your chemical reaction, you are basically going to do what? You are going to apply the Nernst formula and getting the value for. So what is happening? Let me write completely so you don't get confused. This is your oxidation. So oxidation half cell, what is happening? Mg from solid is getting converted into Mg2 positive aqueous by losing 2 electrons. On the reduction half cell, what you are observing? Your copper from 2 positive aqueous is gaining 2 electrons and converting into copper solid. So the net chemical reaction, what you are going to get? Electrons are going to get cancelled out. Mg
Yes, sir.
solid plus copper 2 positive aqueous is giving Mg2 positive plus copper solid. So to this equation, this is a balanced chemical equation. You have to now apply the Nernst equation. So what does Nernst equation says? It is basically E cell is equal to E naught cell minus 0.0591 divided by N log theta, right? So tell me what is the value for N here?
4.
How? How many electrons
Sir,
you are
2.
observing? Two.
2.
So for N you have two. What about theta? How you are going to calculate the theta? Tell me. How you are going to calculate the theta? See, for theta, what we know? Theta is basically product concentration to the power stoichiometry, reactant concentration to the power stoichiometry. Right. In the production side, what do we have? We have Mg2 positive and Cu. So I told
Yes.
you that the solid thing is going to get basically the value is unity, which is 1, so we don't have to consider it. So what we are going to consider only the aqueous thing, which is Mg2 positive, right?
Yes, sir.
Aqueous. We
And
will write it like
CO2.
this, divided by
CO2
copper.
negative. No, CO2 positive.
Is it clear? Can we
Yes,
use
sir.
this here?
Yes, sir.
Okay, that's good. So I am going to use this, divided by, right? So now look at the question carefully. They have given you the concentration for your Mg2 positive and your copper 2 positive. So you are going to use the concentration value from here, right? So for Mg2 positive, what is the value? 0.001. For Cu2 positive, 0.0001. Right. So I'm going to take the values here like this. Right. So what is the value here? For Mg1, 0.001. For the Cu1, 0.0001. Is it clear till this point?
Yes, sir.
Now, one more thing that you should remember. I told you how you can calculate the E naught cell value. I told you it is nothing but E cathode minus E anode. But both of them should be in reduction potential. Do you remember this or not? How can we calculate the E
Yes,
naught cell
sir.
value? So, see, let us go back. We have magnesium and copper, right? So, what is the reduction potential value for magnesium? It was magnesium, right? It was magnesium. So, for magnesium, we have this value,
Yes, sir.
which is in reduction potential. This is the tendency to get reduced. It is gaining the electron from the other species. It is minus 2.36. What about the next? What about the other one? Copper. Copper has 0.34. If you have these two metals, out of these two, which one will be behaving as a cathode and which one will be behaving as an anode? Out of these two, which one is stronger? If these two guys have
Copper.
electron, copper, good, good, good. So you will make it cathode and you will make it
Anode.
anode, right? So
Yes, sir.
from this data, you can calculate the E naught cell as well. At the standard temperature and pressure, standard condition, you can calculate the E naught cell, which is this thing. So what we have, E cathode 0.34 minus 37. After solving this, what you're going to get? 2.71. So now you have E naught cell as well. You have this, you have this, you have this, you have this. So basically now you have to do the maths and you will get your E cell value as well. Minus 0.0591 divided by 2 log. Can I write it like this? 10 to the power minus 3 divided by 10 to the power minus 4. Can I do this?
Yes.
Now, can I write it like 10? Because 10 to the power minus 3 plus 4 is 10, right?
Yes, sir.
So how much is log 10?
1.
0.0591 divided by 2. So after solving this, you are going to get 2.71 minus 0.0295, and the E cell value you are going to get is 2.68 volt. So that's how you're going to do the Nernst equation formulas question. Okay.
Yes, sir.
So you have to do this as homework. The next one is homework as well. And the next one is homework as well. Okay, these three are homework. The same funda that you have to apply. The thing is, you should always use the balanced chemical reaction. If you are not balancing it, you will get the answer which is going to be wrong. Okay, so try these three questions. The funda is again same, and you can hopefully do it. Is Nurse equation clear?
Yes, sir.
Okay. Now let us move ahead. This is Latimer diagram. I don't think it is in your NCERT, but let us understand it. It might help you to solve some questions. So let us see what is Latimer diagram. Just give me one minute. What is Latimer diagram? Suppose you have given basically two or three sort of chemical cells in different oxidation states. So by relating two cells, you can determine the value of third one. It is simple as that. Suppose what is happening here? Reduction or oxidation?
Uh, Oxidation.
See again.
Oxidation.
Oxidation or reduction? From two positive, it is gaining some electrons and getting converted into a solid thing. It is gaining electrons.
Reduction.
What about this one? Is it oxidation or reduction?
Uh, Oxidation.
Good. Now we have to find this one. This is oxidation or reduction.
Reduction.
Okay. Now what you can do here is, see, you have started with Cu2 positive and you have directly gone for Cu. So not by doing the entire thing, you can cut it in short steps. So you will start with Cu2 positive, then you will go to Cu positive, then you will go to Cu, right? Now the good
Yes,
thing
sir.
about this is you have the values for the small parts. Suppose you have the value for Cu2 positive to Cu, which is given as 0.34. Okay. And what else do we have? Cu positive to Cu2 positive. From here to here, we have value again, which is given as this, right? Now, one thing that I would like to ask here is this is given in oxidation, but to make the entire thing simple, which type of redox type, which type of reaction do we use? We convert it into reduction, right? So how can you convert E oxidation into E reduction? If you have a E cell in oxidation potential state, how can you convert it into a reduction potential state?
Uh,
Tell me. Tell me, Ali. If you don't know, let me know that as well.
no,
See, you have to go to the PDF. It is written, right? If you have E reduction potential, you can just simply use a negative sign and you can convert it into E reduction potential, right? So this thing is in oxidation, but here, if you see carefully, if you are going from here to here, then this is reduction, oxidation from Cu positive to Cu2 positive, but we are going in the left direction. So from here to here, we have to use the reduction, right? So to convert this oxidation thing into reduction, what you are going to do, you are going to just multiply it by plus, minus sign, and minus minus is going to be plus or not.
yes, sir.
So you have your value here. Now, what you need to find Cu positive to Cu. From here to here, you need to find. So what you are going to do? You will do N1 E1 plus N2 E2 plus is equal to N3 E3. So how we are going to do this? one more thing. This is n. So from this point to this point, how many number of electrons we have gained? 2, because from Cu to
Yes, sir.
positive, if you gain 2 electrons, you are going to get Cu. So the n value is 2 here. You have to determine this. Let me mark that as well. This you need to find. So E1, N1 plus N2, E2 is equal to N3, E3. You have N1 is equal to 1. If you are going from this value to this is your N1 step. This is your, again, the number of electron is 1. From Cu2 positive to Cu positive, the exchange of electron is 1. From Cu positive to Cu, the gain of electron is 1. But from Cu2 positive to Cu, the gain of electron is 2. I hope it is making sense or not.
Yes, sir.
So here N is 1. The E1 is given, which is 0.13. 0.13, right? For this one, you have to calculate N1 E2, sorry, N2 E2. Let me write it. This is your N1, this is your N2, this is your N3. Okay, so you have to calculate this one. So you will put it here, E, and you have given that N3 one as well. So after solving this, you will get the value for your E. Basically, just relate. You have to relate. Okay. So how
Yes,
much
sir.
value you're going to get is 2 into 0.34. This thing will go on the opposite side. 1 into 0.153. After solving this, you will get your E cell value of the third cell. Okay.
Yes, sir.
See it for a few minutes, then we will move on. This is the calculating K equilibrium is the last topic. Then we have covered the half portion of our chapter, and we will move. Like we might be able to end it today itself.
Done, sir.
So now, continuation part of our Nernst equation. Suppose your reaction is at equilibrium, right? If the reaction is at equilibrium, your E cell is going to become 0. Your E cell is going to become 0. Okay, what is happening? Just give me a second. Okay. So if in your question they have given the equilibrium condition, so what modification you can make to your Nernst equation? At equilibrium, your E cell is 0, because at equilibrium you are not observing any sort of reaction. The things are at equilibrium, they are not moving. The electron exchange has stopped. There is no redox reaction that is occurring. So at equilibrium, what you can say, your E cell will become 0 and your reaction quotient will become K equilibrium. Okay. So basically your reaction quotient becomes K equilibrium. Both have same meaning. but this K equilibrium is signifying that your reaction is at equilibrium. So your Nernst equation will basically modify into this formula. How is it? E cell is equal to E naught cell minus 0.0591 divided by N log theta. So you will basically replace theta by K equilibrium, and this thing is going to be 0. So you will keep it here and you will move the entire thing on the left hand side. So you will get something like this. So this is the modification of your Nernst equation if the conditions are at equilibrium. Okay.
Yes, sir.
Now the Nernst equation part is complete. Now we are into the conductance part. Let me see. So now let us move to the conductance. Conductance of electrolytic solution. Okay. So what is basically conductance? Conductance is the ability of an electrolyte to conduct. A question for you: if you have a metal, what is the basically thing that is responsible for the electricity? What is causing the electricity in metal? What is the reason of electricity in metals? What makes electricity?
Electrons.
Electrons, right? Good, good, good. Electrons move in metal, and in the opposite direction, you observe current. But what if you don't have a metal? You have a solution, an aqueous solution. So in aqueous solution, we never say that the electrons are causing the electricity. In aqueous solution, in in liquid state, the thing which is responsible for carrying the current is ions. Okay. So what is an electrolyte? Electrolyte is something which is basically able to produce ions, which are responsible for the conductance. So what is conductance? Basically the ability of electrolyte to conduct. We have two types of conductance. One is metallic, or you can say electronic conductance, and the other one is the electrolytic or ionic conductance, which is the entire concept of this chapter, which is the entire thing that we have to learn. This metallic part, you will learn it in your physics class. So let us differentiate between these two. In metallic conductor, the charge is carried by electron, but in electronic, the charge carriers are ions. It may be cation or anion. In metallic conductor, you don't observe any chemical change, but for electrolytic conductance, you observe some change. For example, decomposition of electrolyte. You started with an NaCl, right? You have namak in your home, right? After you dissolve it in pani, what you observe? The salt basically dissociate. Its composition is getting changed. It is doing a chemical reaction with your solution. So decomposition is observed. Decomposition of electrolyte. In metallic conductor, no transfer of mass is observed, but in electrolytic, transfer of mass is observed. Basically, ions are traveling. Am I audible?
Yes, sir.
The fourth point is resistance in metallic conductor is due to the collision of electron with fixed metal atoms. The electrons are moving inside the metal, and metal has its own atom. So the collision between your electron and metal's own atom is causing the resistance. But in your electrolytic solution, what is the cause of resistance? Resistance is due to the collision of ions with solvent molecules and interionic forces of attraction. You have your ions, which are causing the electricity, and your solvent, in which your ions are traveling, has their own atoms basically. So solvent molecules and your ions are getting collided, and this is the reason of what? Resistance. Also, your ions have some sort of charges, and in your solvent molecules will also have some sort of charges. So they are going to have some attraction as well. If my ion is moving in certain direction, my solvent molecule will try to attract it and causing its speeds to slow down, basically creating a resistance. So these are the two reasons of resistance in your electrolytic solution. Is it making sense?
Yes, sir.
Okay, let us talk about the next one. If you have a metallic conductor, if the temperature is high, the resistance will also be high. But for ionic, it is is what we call it, inversely proportional. Temperature and resistance are inversely proportional for your electrolytic, but for metallic it is directly proportional. How? Suppose if you are charging your phone is having some metallic type of structure basically, right? Electrons are responsible for the electricity. So while you are charging your phone and the temperature in your room is high, you haven't turned on your AC. So what you will observe? The first thing is your phone is going to get up heated and the charging might be a little slow. But if you are charging your phone in your AC room where the temperature is maintained, you will observe the phone is not getting heated. On top of it, the charging is pretty smooth. So at higher temperature, what you are observing, the resistance is higher as well. But for your
Yes, sir.
electrolytic, it is inversely proportional because it is in aqueous state. If you are increasing the temperature, the ions are going to move away. If the ions are moving away, if your solvent molecules are moving away, they are creating a space. They are creating some space for your ions to travel freely. If they are traveling freely, they are easily able to conduct electricity. Is it clear?
Yes, sir. Yes, sir.
Now, what does they depend on? The metallic part, it depends on the metal, nature of metal basically, number of valence electron. If the electrons are more, the electricity will be more, and the temperature. For your electrolytic solution, they will depend. The electricity, the conductance will depend on the nature of electrolyte. Uh, we have basically two type of electrolyte. One is strong electrolyte and one is weak electrolyte. What is a strong electrolyte and what is a weak electrolyte? Can you differentiate between these two? Difference between strong and weak electrolyte. Am I audible, Ali?
Yes, sir.
What is the difference between strong and weak electrolyte? If you don't know, just let me know, na, and then I will tell you. The thing is, this thing I told you in the first class itself. If you remember. See, let me tell you. A strong electrolyte is an electrolyte which is getting dissociated completely, right? And if it is getting dissociated completely, whether it is going to conduct more electricity or less electricity, tell me. If your electrolyte is a strong electrolyte, that means it is getting dissociated 100%. If it is getting dissociated 100%, it is generating the maximum number of cation and anion. If in your reaction there are maximum number of cation and anions, whether it is going to create maximum electricity or minimum electricity,
Maximum.
right? So if your electrolyte is strong, you will get more conductance. If it is weak, you will get less conductance. The second point is size of ions and their solvation. If your, this is, we can relate it with organic. So while we were discussing the haloalkane chapter, we came across the point where we were dealing with solvation. What is solvation? Mhm. Okay. So let me ask you a easier question. Which ion will travel faster? A big ion or a small ion?
Small ion.
So if your ions are small, whether you are observing more conductance or less conductance? More. So size of ions are also an important factor to determine conductance or not. Okay. The next point is nature of solvent. Which type of solvent you are using? What kind of attractive forces it is going to impart on your ions. So again, nature of solvent is important. Solid-solid interaction and again the temperature. So these are the some factors which are going to depend, which are going to basically, what you can say, which are going to cause some effect on your conductance of electrolytic solution. Right. So I would like you to take few minutes to read these points from starting to end. Then we'll move to the next thing. How many types of conductance do we have, and what are the factors, and what are these things are basically. So try to read it and let me know once you're done.
Done, sir.
Okay. Now, so let us talk about resistance of electrolytic solution. I hope you are familiar with this formula, Ohm's law. What is Ohm's law? V is equal to IR. So with that, we can derive this R is equal to V by I or not. This is basically Ohm's law, right?
Yes, sir.
Now, what else do we know? We know that your resistance is equal to resistivity, length of your wire divided by area of your wire. How did we derive this? You might have heard this thing. Let me show you. That your resistance is directly proportional to what? Length of your wire, and it is inversely proportional to area of your wire. If you are removing this proportionality sign, you have to introduce a constant which is resistivity. So you have derived this from here. Basically, your resistance is directly proportional to the length of your wire and inversely proportional to the area of your wire. Okay, and this constant is resistivity. Is it clear? These two formulas.
Yes, sir.
Now, what is this rho thing? This rho is representing resistivity here, or you can say specific resistance. Its SI unit is ohms per meter. Sorry, ohms meter, not ohms per meter. How? Let me show you this again as well. If you are keeping this here and you are sending the thing like this. What is the SI unit of area? Meter square. What is the SI unit of resistance, which is ohm? This is meter square, and you are dividing it by length. Length is meter. So this is how you get the SI unit for your resistivity. Resistivity, or you can say specific resistance. Is it clear?
Yes.
So let us read this point. If a solution is placed in between two parallel electrodes having cross-sectional area A and distance L apart, then you are going to apply this formula, which is resistance वाला जो हमने ऊपर देखा. Okay. So now this is what? Resistance. But what we need to find? Conductance or conductivity. So let us see how we are going to derive our conductance formula with this resistance formula. Okay. So if this is specific resistance, what is going to be the specific conductance? So if this is specific resistance, and we now have to find the specific conductance, or you can say conductivity, opposite of resistivity, and it is shown by K. It is a symbol basically, and it is kappa. So conductivity is measured in kappa, K. So basically, the reciprocal of your resistivity or reciprocal of your specific resistance is conductance or specific conductance or conductivity. Reciprocal of your resistivity is conductivity. Okay. And it is represented by K, and K is kappa. So the resistivity is given by what? Resistivity is R A by L. And if you are doing the reciprocal of it, what you are going to get? You are going to get this. And the reciprocal of this thing is your kappa, which is conductivity. Is it clear? What are we doing here? Or do I need to write it? Let me write it. So we started with this. Then we took only resistivity. And what is resistivity? Sorry, what is conductance? Conductance is basically K. K is kappa, which is showing conductivity. And it is nothing but 1 upon basically reciprocal of your resistivity. So if this is your resistivity, and if you are doing 1 upon resistivity, you have to reciprocate the entire writing as well. So it is 1 upon R into L by A. And this is what? Kappa. So you are basically writing it like K L A R. Is it making sense? How we
Yes,
derive the
sir.
conductivity from your resistivity? It is nothing but reciprocal of your resistivity. What is going to be the SI unit of it? See, the SI unit of resistivity is ohm per meter. Sorry, ohm into meter. So if you are reciprocating it, what you are going to get? Ohm inverse into meter inverse. Or if you are using centimeter, then centimeter inverse. And one more thing that I would like to add here is 1 upon ohm is nothing but Simon. So you can write it like ohm inverse, or you can use the term Simons, which is S. Okay. So opposite of ohm is Simons. Simon is something which we measure to calculate conductivity, and ohm is something we measure to calculate resistivity. Is it clear? What is Simon?
Yes, sir.
So how does kappa is affected? How does conductivity is affected? So conductivity increases with increase in ionic concentration. If your ions are increasing, that means your conductivity is also going to increase. And your kappa, which is conductivity, increases with speed of ions. If your ions are moving with high speed, then they are carrying more conductivity. But what does kappa, like, what is the factor that kappa decreases? How conductivity is decreasing? If you are doing dilution, then your conductivity will decrease. So these are the factors which affects the conductivity, your kappa. Concentration increases, kappa increases. Speed of ion increases, kappa increases. But dilution increases and kappa decreases, which is conductivity. Okay,
Yes, sir.
is it clear? So see this for like 1 or 2 minutes, and we'll move on. If you have any doubts, Celia, then please let me know and ask.
Then, sir.
Okay. Now we know what is resistivity and what is conductivity and how the conductivity is going to get affected. So now let us see how you are going to calculate the conductance of an electrolytic solution, measurement of conductance of electrolytic solution. Okay. So let us accurate measurement of an unknown resistance can be performed on a Wheatstone bridge. Have you heard about this Wheatstone bridge thing? You might have seen it in
Yes,
your
sir.
physics lab. So with the help of Wheatstone bridge, you can calculate the resistance of a metallic system, metallic circuit. However, for measuring the resistance on an ionic solution, we face two problems. In aqueous solution, we cannot make Wheatstone bridge because it is an entirely specific phenomena for your metallic conductance. So if you are measuring the resistance of an ionic solution, we face two problems. The first one is if you are passing direct current changes the composition of solution. If the composition of solution is getting changed, then it is going to affect in measuring while you calculate the conductance of the solution, right? The second problem is a solution cannot be connected to a bridge like metallic wire or other solid conductors. In a solution, you cannot make a bridge type of thing, right? The way you do in the Wheatstone bridge, in solution, you cannot do that. So we face two type of problems. The first problem is solved by connecting AC current. Rather than using DC current, if you are using AC current, then your solution is not getting decomposed. Its composition is not changing. So the first problem is solved. But for the second problem, what we have to do? For the second problem, we basically create a specially designed vessels which we call conductivity cell. So to solve the second problem that we cannot make a bridge in our solution, we use a conductivity cell which is specially designed for our conductance of ionic solution. So how we are going to create this conductivity cell? With the help of our conductance formula. So let us see what we are going to do. So this is your formula for conductivity, which is kappa, right? Which we derive. Am I audible now?
Yes, sir.
Okay, so what was the last thing you heard? What was the last thing you heard, Ali? Hello?
Yes, sir.
What was the last thing you heard?
Sir, my internet went, that's why.
No, I understand your internet is not working properly. I was asking what was the last thing you heard? Like, so if you might have missed the measurement of conductance of electricity part, then I will repeat it. What was the last thing you
Sir,
heard?
you just started this. You just started measurement of conductance. Then
Okay,
it
so
went.
let me repeat this sentence. So now we know something which is kappa, which is basically determination of conductivity, right?
Yes, sir.
So what we need to know now? We need to know how can we measure this conductance in a practical way, right? Like by creating something. Suppose the accurate measurement of an unknown resistance can be performed on a Wheatstone bridge. You might have seen in your physics lab something called Wheatstone bridge. And in Wheatstone bridge, you can calculate the resistance, right? The electronic conductor, metallic conductor,
Yes,
basically
sir.
metallic resistance. But if you are doing the same thing, if you are calculating the resistance in your ionic solution, you face two type of problems. The first one is if you are passing DC current in your Wheatstone bridge, you pass DC current, right? If you do the same thing in ionic solution, your composition is going to change. The solution's composition is going to change, which is going to affect our conductance. So this is our first problem. We cannot use the direct current. The second problem is a solution cannot be connected the solution cannot be connected to the bridge like a metallic wire or other solid conductor. In a solution state, you cannot make a Wheatstone bridge type of conductor because in your solution you cannot make a bridge basically, right? We cannot use a metallic sort of structure in your solution state. It is not going to work. So the first problem, the DC current problem, is solved by using AC current, right? The second problem is solved by using a specially designed vessel, which we call conductivity cell. So now we have to understand what is this conductivity cell actually. Okay. The first problem, the DC current we cannot use in ionic solution, we use AC current. The second thing is as we cannot make the Wheatstone bridge type of like bridge basically in solution, we use vessels, conductivity cells. How we are going to create this conductivity cell with the help of our kappa formula, conductivity formula, right? So this is the formula that we derived from the resistivity or not.
Yes, sir.
So this length divided by area, you are going to consider it as G. And this G is nothing but your cell constant. So by taking your length and area as a constant, you are going to create a thing which we call cell constant. And this cell constant is basically your conductivity cells constant, which is going to help you to determine the kappa conductivity. Okay, this is G. G is nothing but L by A, which is cell constant, and the SI unit is going to be centimeter inverse or meter inverse. The SI unit is centimeter inverse. So the new formula for your conductivity is G by R. Okay, your G is centimeter inverse. Is it clear what we did? If you have any sort of doubt, please ask me.
No, sir.
Sure.
Yes, sir.
Okay. Hmm. So now we covered what is conductivity. Now we have another term which we call molar conductance. As the name suggests, what is molar conductance? Conductance of all ions by 1 mole of electrolyte when dissolved in a certain volume is called molar conductance. Conductance of all ions by 1 mole of an electrolyte. If you are using 1 mole of electrolyte, all the ions that are produced by this 1 mole of electrolyte, when you are dissolving it in a certain volume, this is going to be called molar conductance. Okay.
Yes.
Your molar conductance is represented by lambda m, and it is nothing but your simple conductivity kappa into a certain volume, which is V. Your kappa's SI unit is Simon centimeter inverse. Your volume SI unit is centimeter cube. And after solving, the entire thing's SI unit is going to be what? Simon centimeter square per mole inverse. You might be wondering how we derived uh, like this K into V into this K into 1000 by M, right? Because in this formula, we don't have anything which we can use to determine or relate moles with. But as molar conductance is given, we need something which is using molar term. So how we did this? So lambda m, which is your molar conductance basically is conductivity to volume. And if we go back, what is the formula for molarity? Number of moles divided by volume in liter. Volume solution in liter, right? This is your molarity or not?
Yes, sir.
So in the formula, you have given volume. And in your molarity formula, you have volume as well. One more thing I would like to show you here is what is the value for N? For molar conductance, what is the value for N? Number of moles are taken to be 1. So you can use 1 here or not. So the
Yes, sir.
formula for molarity is going to be M is equal to 1 upon volume in liter. Is it clear till this point or
Yes,
not?
sir.
Now, I can do this or not. I will put the volume on the left hand side and molarity on the right hand side. Can I do this or not?
Yes, sir.
Now, what we know, if you have to like basically convert liter into centimeter, basically milliliter, what you can do? You will divide it by 1000. So volume Basically, if you have to find it in centimeter inverse, what you are going to do is, you know, na centimeter cube is how much? 1 milliliter. So what you're going to do is, if you are converting this into milliliter, or you can say centimeter cube, you will have to divide it by 1000 is equal to 1 upon m. And after solving this, you are going to get volume in centimeter cube or volume in milliliter is equal to 1000 by m. So what you did, you just replace your volume value with 1000 by m because you know the formula for molarity. You just interchange your volume in terms of molarity. So you can use the mole factor. Is it clear how we derived this formula from this one?
Yes, sir.
Are you sure? Please see it carefully. And if you have any doubt, please let me ask. Oh, please ask me because this thing is very important and you are going to get so many questions from it. You should be clear.
Done, sir.
See, how much is 1 centimeter? It is 10 to the power minus 2 meter. Centimeter cube 10 to the power minus 4 meter square. Sorry, centimeter square is equal to 10 to the power minus 4. Centimeter cube is nothing but 10 to the power minus 6 meter square. So in rare occasion, they might ask you the molar conductivity in meter cube or meter square. So if they are giving the data in centimeter, you are going to use this formula. If they are giving the data in meter, then you have to use this formula. How we derive this one? It is very simple. So what is centimeter? See, here you have centimeter cube. This is your formula for volume in terms of centimeter cube. But what if they are giving it in terms of meter? So you will just do what? How much is 1 centimeter? It is 10 to the power minus 6 meter square. So you will put what? V, if you have to convert it into meter square, you will do this into 10 to the power uh, 10 to the power minus 6, which is going to be what? Is equal to 10 to the 1000 divided by n. This is in meter, right? Now, if you are sending this thing, or basically you can write it like this, V meter square into 10 to the power 6 is equal to 1000 divided by m. And if you're sending this thing to the left right hand side, what you are observing, meter cube is equal to 1000 divided by 10 to the power 6 into m. You are going to get 1 upon 10 to the power 3 m. So this is the formula you derive with the help of that one. Just simple unit conversion, right? So what you can learn, if you need to learn, is in centimeter, the 1000 is going to be the in denominator. Sorry, numerator. For meter, it is going to be in denominator. Okay.
Yes, sir.
So what I'm going to do is, as you are traveling, I will keep the things still here. In the next class, we are going to discuss the effect of dilution or molar conductance. And the thing that I would like to tell you here is the relationship or the effect of dilution or your simple conductivity is opposite if you compare it with molar conductivity or molar conductance. Okay. So let me give you a brief and let me give you it as homework. See, in kappa, where is kappa? Kappa decreases with dilution. your normal conductivity decreases with dilution, but your molar conductivity or molar conductance increases on dilution. You have to find out the answer why. This is your homework. Write it somewhere. Why uh, K, which is conductivity, decreases upon dilution, but your molar conductivity or molar conductance increases upon dilution. Okay, this is your homework. I would ask you in the next class, and I hope you will be able to, like, you can use any source. I just need the answer, right? Why, what could be the reason? Is the question clear?